So I sort of changed the titles because I had to move some stuff from lecture 4 into 5. So I'm going to talk about pseudo mom- momentum, which picks up on the Hamiltonian stuff, and talk about the Hamiltonian description of fluids, and then how this connects to waving flow interaction, and how this is part of the turbulence problem in the end. Um, and actually, some of you know Michael McIntyre. So when I was a PhD student, I was discovering Andrews and McIntyre and whatnot, and I came across this paper, and how many papers quote Alice in Wonderland, you know? So I decided I've got to do a postdoc with this guy. So it's a very interesting, very philosophical paper, and I do advise you might want to go read that. But now I'm going to switch to the we can switch to the board for a while, and I'm going to can we raise this? Okay, I think maybe we haven't quite seen this, so I'll write it out at the risk of being a bit pedantic. The barotropic beta plane, so F is F naught plus beta y, and y is the latitude. So I think there's been references to this. Hank talked about the equatorial beta plane because the equatorial F plane makes no sense. Well, actually, people do use the non-rotating. You probably heard about that last week. So actually, for a convection, people use an equatorial F plane. But certainly, if you're interested in the waves, you would use equatorial beta plane. And similarly, there's the barotropic beta plane. We're going to think of this as away from the equator. And of course, you implicitly need to have a length scale that's going to be much less than F naught over beta. Otherwise, you ought to be on the sphere. So we linearize about a constant zonal flow U, and you get d by dt of del squared psi plus U d by dx del squared psi. That's the Doppler shift term and the beta term. And you substitute the Ansatz exponential of I to the kx plus Ly minus omega t. You seek solutions. It implies that you get frequency is uk minus beta k over k squared plus L squared. So this is the famous Rossby wave dispersion relation that probably all of you have seen, but maybe there's a few that haven't, because I know there's people that are working in areas of turbulence that don't necessarily connect to the large scales. Not in this one. So sometimes you include a deformation radius, but this is just the sort of simplest non-divergent case. So if you're interested in a longer, so there could be another one, and then you get a 1 over LR squared. That's right. So there's a generalization, but we don't use that in the atmosphere typically. So this is the sort of simplest case. Okay. Now, so these are Rossby waves, and I think the first thing that's kind of interesting, if you were just discussing Rossby waves to someone that knew, say, a physicist, it's unidirectional. That's actually kind of unusual in the sense that most waves come in pairs, right? Sound waves, inertial gravity waves, but Rossby waves, like Kelvin waves, like these equatorial lower frequency waves, have a single root. So they always propagate. You always see that there's always a negative intrinsic frequency, so the phase speed is always westward relative to the mean flow. But of course, these are very important because they account for the stationary and the low frequency features of the atmosphere and the ocean. Of course, you also have to include Kelvin waves if you're in the tropics. So that's clear. And if you ever lecture about low frequency or stationary waves or low frequency variability, you're always going to talk about Rossby waves. It's also the case, of course, this dispersion relation, and I should say, of course, in a stratified system too, which I'm not going to talk about here really, but not in terms of the theory. Then there's just like actually with the deformation radius, you get a vertical wave number here to do with the vertical modes as well. So there's baroclinic. This is a barotropic Rossby wave. There's baroclinic Ross waves, but they have the same. All you do is add an extra term down here in the denominator. But these are also, and it's perhaps not as well known, also the building blocks of synoptic scale eddies. By synoptic scale, we just mean the daily weather systems that are highs and lows of wavelengths of or scales of a few thousand kilometers. Synoptic scale eddies. This is what I'm calling macro turbulence in this context. Though if it's turbulence, it's not waves, right? Although you can argue, and actually, usually someone mentioned a word war in a different context. Usually, when scientists are engaged in wars, it's about semantics. I mean, often. So, but these are clearly not linear waves. I mean, you've got closed PV contours, all sorts of things that don't look at all like waves, coherent structures. But it's important, as it turns out, it's important for understanding the wave and flow interaction problem that comes from this. Do you need to see? Well, I'll do it very quickly. The atmospheric dynamicist view of a Rossby wave. So Hank gave the oceanographer's view of the Ross wave, which is in terms of the temperature or the mass. Well, you said you shouldn't think of mass, but you can think of course, in a shallow water, you can think of mass as sort of mass field view of it. You can also think of the vorticity view, and of course they're related because they're just different parts of the potential vorticity. So you imagine you have, say, latitude in this direction and x in this direction, or longitude, and you have the sort of background beta effect, and then you just move a PV gradient. So this is a line of constant q, which is del squared psi plus beta y, and so if we call this zeta, the relative vorticity, and we know that beta means that so we have a positive gradient of the planetary vorticity here. So if you move contours up here, you know that the relative vorticity must be positive. Sorry, I almost get this wrong. Negative, because you've got more planetary, so therefore less relative, and this is positive down here. So then the vorticity is the curl of the wind field, right? Use the right-hand rule. So this means that you're going to have velocities that act like this, and this is going to push this PV contour down, and this is going to force westward propagation. So this is textbook view of the Ross wave, which I apologize most of you. Do I have that wrong? Oh yes. I don't think well on the blackboard. I don't know how I survived 25 years in the classroom, but very good. Yeah, so this is going to push this up, so then you're going to get, if you think of a phase, this is going to move this way, and then this is going to move down, so it's going to move that way. Thank you. Okay, so now that's just very, very quick background. Now we jump to the Hamiltonian stuff as promised. And actually, I'm going to forget beta briefly. I just wanted to put this down. No, I'm the kind of person who, if you ask me a question, I like to go away and think about it and come back. So it's a terrible job to be a professor. Okay, so I said the reason that we're doing Hamiltonian stuff actually is that it's relevant to fluids, and in the case of, if you're interested in wave beam flow interaction, which is an adiabatic, at least the first approximation. You're concerned about the rectification terms. You're concerned about the role of the nonlinear, the advective nonlinearity. It's all part of the conservative part of the system, which is the Hamiltonian part. So just as Hank has used the dynamical systems and bifurcation structure as a backbone of a hierarchy, I found that the Hamiltonian structure is a very, very important backbone of the hierarchy for wave and flow interaction. So it's actually not that difficult. I mean, there's a lot, you can get into very complex stuff very fast, and by the time I left Toronto, there are actually quite a few mathematicians doing Hamiltonian fluid dynamics, but I just couldn't understand them at all. So it can get very abstract very fast if you want. But I'm a prosaic kind of person. Okay, so our equation, I'm going to write it this way, actually. So forgive me, I'm changing notation, but so we can write the vorticity. I guess I'm using V's here, aren't I? Sorry. The advection, which you can write as a Jacobian. Okay, so first thing that you do is, well, we know what the Hamiltonian is. The Hamiltonian is the energy, right? And we know what the energy is for this system. So what you want to do is you have to compute. So we had these gradients of our state vector, right? We had the u was the symplectic notation. U were the q's and p's. Well, here we're going to have, it's a PDE. So rather than the index I, we're going to have the coordinates x and y, and we have to use a variable that's analogous to the u. So it could be either psi or omega. Those are kind of obvious choices. You probably know omega is somehow more fundamental, so it turns out it's written in terms of omega. So let's see what happens if I vary this. So you've all done a bit of variational calculus, I hope. So if I just vary this, so of course the half grad psi, so we get del psi dot delta del psi. Okay, so but now I want to express this as something times of a variation of a quantity. So I have two choices. I could either want to vary psi, or I could vary del squared psi. Well, del squared psi is going to be the choice we use. So I have to integrate by parts. So I get del dot psi delta del grad psi minus psi delta omega. Now this is assuming boundary terms vanish. So of course that'll be the case if you're in a doubly periodic geometry, which often people are. But if you have channels, let's say, then just like for as I was explaining yesterday, that's fine. It's not a problem. Then you pick up a boundary term, but there'll be psi is constant on a rigid boundary because there's no flow across the boundary, and then you have a variation in the gradient of psi normal to the boundary. That's the flow along the boundary, and that integrates to the circulation. So if you want to do this in a channel, then you wind up getting variations of the circulation as well. But you've got a conservation law for those. So I'll just forget those and cross this out. And then what we have is just that so this is what's called the functional derivative of h with respect to omega is psi, because it's the argument, it's just the argument of the variation, right? So delta h is the integral over the space of delta dh d omega delta omega dx dy. That's by definition. That's the definition of a functional derivative. So we get this relationship. Okay, does everyone follow that? I mean, if you do variational calculus for extremization, I mean, probably people have done this kind of thing before. So you're used to variational derivatives. They're called functional derivatives in this context usually. So we pick off that there's a derivative. So this is the analog. So I'd say just as in, these are the infinite dimensional analog of partial derivatives. So as I say, in a finite dimensional system, you just have partial derivatives, and you have these. We have the indices, the pi and qj for the canonical system, or ui for the non-canonical, or the generalized Hamiltonian system. Here we just, rather than fixing I and j, we fix x and y, and then we just vary the vorticity. Well, so you can think of varying the vorticity, and we multiply that by the functional derivative, and that gives us our answer. But of course, it's what I want to write down. But of course, they can reflect the non-local properties. So it's very important. This is not a partial. This is the variational derivative, and to figure out what it is, you usually have to integrate by parts a few times. So non-local properties. And in some sense, you would say this is like PV inversion. You have this non-local response. Okay, so how is this Hamiltonian? So I'll just point out that this can be written in symplectic form. As the omega by dt is equal to j, and I'm using j now as this, not as a Jacobian. I'll use this symbol for that. J, it's like my previous j, where j is minus, it's an operator, Jacobian acting on this. So just to step through, first of all, we just show that this works. So I know the functional derivative of the Hamiltonian with respect to vorticity is minus stream function. I substitute minus stream function in here. I have two minuses, so I just get that d omega by dt is Jacobian of omega and psi, which is, of course, minus Jacobian of psi and omega. So this works. How do I know it's really Hamiltonian? Well, I have to show that this j satisfies all the required properties. Well, it's pretty obvious to see skew symmetry and so on. The crucial one actually is this Jacobi identity, which I won't go into, and it was known to Arnold and so on. It's known by mathematicians. Actually, we wanted to prove it for ourselves, so I wrote one paper with McIntyre when I was at Cambridge, and there's an appendix where we just go through brute force and show Jacobi's identity. So if you're interested in tracing it through and kind of simple notation, you can do that. So I just want to take that as given. The interesting, the thing is that these different, and I've written review papers on this. That actually I've sent Antoine. I gave a whole week of lectures on Hamiltonian GFD at the Woods Hole Summer School, almost 25 years ago, 1993. So we can put those up, and you can look for that. Sort of goes through all this thing in detail. And you can write this for the Boussinesq system. You can write it for the primitive equations. You know, you can every proper PDE system that we use in GFD has a Hamiltonian structure with, you know, more and more complex J's here. The thing is, for everything I'm going to show you now on, you don't need to know what this J is. You just need to know that it exists. So that's kind of crucial, that you have this confidence because you know that the system has a Hamiltonian structure, but you actually don't need to know the other complexities of J to do everything I'm going to do from now on. Yep. Oh, I've forgotten all the different. I think it's in those Woods Hole notes, but the hard one is this Jacobi identity. So it's like actually, so you write this in into brackets, and then this is what I don't like. Do I have this? Yeah, I'm not. Sorry, I'm not going to try to make a mistake. But there's this. It's like this thing where you have, A bracket BC plus B bracket CA plus C bracket AB equals 0, and you generate a bracket from this J. So it's a bracket. Okay. Right. So, but in terms of, so I mentioned Casimirs, and so you say, well, what are the Casimir invariants? Well, what we need is that we need J acting on dC because that's our Casimir invariants. We call them C. J is 0. Well, this means that the Jacobian of C and dC d omega 0. And you know that the most general solution of this thing is going to be that this quantity here is some function of omega. That's the general solution of this equation being 0. So we get that dC d omega is some ordinary function, and I'm actually going to write a tilde here of omega. So it's not it's like a true function, like some power law, which means that this C is going to be some other function. Take off the tilde. So these are the Casimirs. The Casimirs are integrals of anything that's the integral over space of an ordinary function of vorticity. Okay, so of course this includes entropy, because that's the vorticity squared, but it includes everything else. It includes cubic, quartic, whatever. And the reason, so we have an infinity of conservation laws. This is kind of interesting because, of course, there's only one Hamiltonian, but there's an infinity of Casimirs, and that actually corresponds to Lagrangian conservation of vorticity. Because you know that, you should know probably that if any function of vorticity is conserved, this follows from, and maybe in fact equivalent to, for all I know, the Lagrangian conservation. Of the vorticity. Oh, just something else. I just wanted to use another function. So, so I could write this as C prime actually. Maybe that's simpler, but of course then you would ask what's C. So if I write that the Casimir is some function of omega, then the functional derivative, in this case I don't have to integrate by parts, right? The functional derivative is just the local derivative, because it's a simple function, and then that's my, but any function of omega substituted in here, this will be 0, right? Okay, so these are the Casimirs, so it's not too surprising. They're just related to the conservation of vorticity. So so now what the other conserved quantity that we tend to care about is momentum, and this is where Noether's theorem comes in. So we have a symmetry in X in this system. So this so we know that we can seek a conservation law. Oh, my chalk's getting a bit short. So we use Noether's theorem. So now the thing is, if you have a solution, now we're talking about a continuous system. So if we have omega versus x, so I will have a trend. So what's the variation in the finite dimensional case with p's and q's? We talked about, say, a change in the coordinate q. Well, here what we're doing is we're shifting the whole field. So we take a field, let's say omega versus x, and we shift it in the x direction. So if this is some field omega versus x, this is omega of x minus, let's say, epsilon, if I shift by epsilon, right? So if I vary omega, that's omega x minus epsilon minus omega x. So that's omega, that's minus epsilon d omega by dx. So the variation that we want to look at is so the variation corresponding to translation in x has a minus sign. That always confuses people, but it's just because of this property. So this is the variation that we want to look for. And now we're going to run another theorem from the symmetry to the conservation law. So this is our this is what we're going to call our delta. I'm going to call this thing m, delta m of, so m will be our conserved quantity. Okay, so this is the variation. We want to find the quantity which generates a variation in omega, an infinitesimal generation, which equals this. So how do I find that? We have to we want just to follow Noether's theorem. We want to, this has got to be equal to dm d epsilon j dm d omega. That's where that formula, rather obscure formula I'd written before, comes from. Now from our j is just this quantity, so we get minus epsilon Jacobian of omega d omega dm by d omega. So the functional derivative of m with respect to omega, the Jacobian of omega, and that has to give us minus d omega by dx. So it should be pretty obvious that this thing equals y, right? So if I put y in there, then I pick off, d by dx, d by dy, so I get a d omega by dx times 1 with a minus sign with the epsilon, which is that, and d by d y d by dx, well, d by dx, so this is 0. So this is the solution. It's not unique because there's a Casimir, so it's kind of a gauge, if you like. But as it happens, the things will cancel in the end, so we don't have to worry about that. The fact that there's a non-uniqueness in terms of, so it's unique to within a Casimir. Okay, so actually this is quite simple. So we now find that but if d omega, if the functional derivative of m with respect to omega is y, then that tells us that m is just the integral of y times omega dx dy. Again, it's just a function of space, so nothing complicated here. The variational derivative is trivial, right? I take the variational derivative as holding y fixed, and I just get the y. Now, how many of you have seen this expression before? A few of you. So this is called Kelvin's impulse. So it's been known for a while. So it may not look to you like we expect momentum, actually, don't we? Because we started with a translational symmetry, but actually you can write this as, so of course omega is dv dx minus du dy dx dy, and if you ignore boundary terms, you get just the integral of u. As I said, you can deal with the boundary terms. It's not that we have to neglect them in these longer notes from Woods Hole I go through with the circulation term and all that kind of stuff. So it is momentum. It's just if you're doing vortex dynamics, which a lot of the 19th century physicists did, this is a far more convenient form because it's local. If you have local vortices, this is easily computable, whereas this thing is way more complicated, actually. So although we tend to think of this as being a more natural form from a vorticity dynamics point of view, this is a way more natural form. So we find that just simple application of Noether's theorem to the translational symmetry, X symmetry, gives us this conservation law. Okay, so I guess it also means so of course you might say, well, okay, this is very cute, but what does it do for us? So where I think, at least personally, I found it, it is satisfying to know that there's a unifying principle to everything. I mean, it's really is nice to know that you can generate, if you're given a very complicated system, as long as you have a translational symmetry, you'll be able to generate something like this. And so you can do this for, of course, any of the models you have. But where I have found this to be most useful, and which I'm going to talk about now, and I think what it relates to the wave turbulence problem that is the main subject of my lectures, is what you might call disturbance invariance. So for me, this has been the most powerful application of this whole principles. Now, actually, if you go read the McIntyre paper on the pseudo momentum myth, you'll find that if physicists were arguing about what's the momentum of a wave, you might say, well, okay, a wave, if you average over x, is zero, so the momentum must be zero. But that turns out to be wrong, because there's higher order effects built in. You can have the same ambiguities with energy if you're in some inhomogeneous background flow. So as long, of course, if everything's very simple, things are simple. But if you have a background flow in there, and of course our states always have a background state. The same issues arise with internal grad waves if you have a variable stratification or something like that. If you have a varying background state, then you can twist yourselves in knots thinking about momentum or energy. But there's a much better way to get it, which is pseudo energy. So let's just, first of all, let's assume that we have a steady solution. Go back to the general case. So U was our general dependent variable. Big U is a steady solution. So okay, then it follows. So du dt is equal to big D du dt, and that's 0. But that's, of course, equal to j dh du at u equals big U. So this thing has to be 0. Now, if the system is canonical, which is what you would normally do in classical mechanics, what you find is that if it's a canonical system, then j is invertible. So then if j acting on this gradient is 0, then it means that the gradient itself must be 0, and that tells you that that the dh du is 0 at u equals 0. So that tells you that h is locally quadratic. So if you do the theory of normal modes in Hamiltonian dynamics, you always wind up with this quadratic energy around the steady state, and you can take a spectrum and look for the modes of oscillation, all those very nice things, because you're in this potential well. But what if the system's non-canonical? So this is not true. So the problem in a canonical system, J is not invertible. So we don't have a condition on the gradient of H being 0, which in general, H is generally linear in the disturbance. So this is a problem because it's not sign definite, right? So this is, if you go to McIntyre's paper, he explores this. We just have one. I just erased it. The rigid body in terms of Euler's equation was a non-canonical system because we have a Casimir. So a non-canonical system is with Casimirs, basically. It's a degenerate J, which means that you have a kernel and you get these Casimirs. And the barotropic vorticity equation is a non-canonical system. Yeah. Well, yeah, like in the that's right. So if actually in the rigid body, if you write the whole thing in coordinates and velocities, then it's a canonical system, P's and Q's. But if you reduce it down to the Euler equations, that's now a non-canonical system. And actually, I will say in fluid mechanics, you can write the equations in Lagrangian coordinates with x's and v's. and then it is canonical, and people have used that. For example, Rick Salmon really exploits that approach, and then you don't have this issue, and then you can work with Lagrangians, different Lagrangian, well, same person I guess, but different. So there turns out that the reduction from the Lagrangian coordinate version of fluids, in which down to the so it's actually it's a reduced system, and actually you eliminate so there's some nice papers on this by Rick and by Pedro Ripa a long time ago. The potential vorticity, in this case, it's a Casimir, right? The Lagrangian conservation of omega corresponds to Casimir. In the canonical representation, it has to correspond to a symmetry, and the symmetry is called the particle relabeling symmetry. So in Lagrangian coordinates, your coordinates are particle labels, and if you can move the particle labels without changing the field, and there is 1 degree of freedom there, which is you basically go around PV contours, so there's an extra degree of freedom, and in that case, the PV conservation comes in explicitly as this particle relabeling symmetry. But I've always wanted to work in the Eulerian frame, which is why I've worked in this, because I think if you want to generalize to primitive equations and more complex models, I think that's much easier somehow, at least for me, in the Eulerian frame. Okay, but we have this general problem. You can see that if the system's non-canonical, we're going to have H being generally linear in the disturbance, and that means it's so it's not sign definite. Cannot define stability, normal modes, etc. So actually, it turns out that that a lot of the arguments about things turned out because of this basic problem. But there is a remedy. Turns out it leads to the concept of pseudo-energy, which I'll talk about. So don't ask me. Well, I will. Actually, I won't talk about pseudo-energy. I'll talk about pseudo-momentum, but it's similar. Actually, it's interesting because when you look at things, this problem, of course, is a fundamental one. So it obviously kept popping up. And I think I mentioned to some people Lighthill's classic book on waves and fluids, and on about page 10 or something, he derives the energy of a sound wave. And if you look at that, of course, if you just derive things from the equations, you don't know what you've used because you've used everything. But in fact, he starts with the energy. He has to bring in a function of the density to actually get a quadratic energy. So to get a quadratic quantity for sound waves, he has to combine the usual energy plus the mass field. Mass field is a Casimir. So so actually he was using Casimirs too, and it was actually effectively a pseudo energy. So these things actually pop up. It's just that they weren't always recognized in right. So I won't go through pseudo energy, but I'll do because we're short of time. But I'll go through the analogous thing for the momentum, because the same issue arises. If a basic state, so here we assumed it was steady, but if a basic state u equals u is independent of x, so in other words it's parallel or something, so that's invariant with respect to translation in x. Then by Noether's theorem, remember du dx is j. Actually, there was a minus sign. Well, actually, sorry, I'm mixing the different u's. I want to be a little careful here. So I want to say, in terms of the previous notation. If this is true, this implies that j dm du at u equals 0. So this is the generalized form. So we have the same issue because this is related to the if there's a symmetry, then we know that the infinitesimal generator, so this thing produces this infinitesimal generator, and if that thing, if there's a symmetry, then this thing has to be 0 at the basic state. So we have the same kind of issue now. We have that m is going to be yes. Thank you. So this is mean that m is linear in disturbance. So again, if you want to compute the momentum of a wave, you're going to find it's a linear quantity, and that's not very satisfying. So what's the recipe? Well, the thing is that if the Casimirs come to our rescue, because if this is true, this is saying that the gradient of m is at this point is tangent. Well, is tangent to the kernel of J, which is filled by the gradients of C. So basically, it means that there will be a C for which the first variation is 0 for some C, right? Because we know that we can. For C, J dc du is always 0. So if this is 0 locally, it's like geometrically you could be, on some sort of a tangent, and I can't do the geometry of this, but it has a geometric interpretation. It means that there's going to be some C for which I can create, for which I can cancel this gradient that's going to rise. Does that make sense? The gradient lies in the kernel of J, which is spanned by the gradients of C. No, this is just momentum. You don't need to. Of course, you can combine them, but this is the simple form. So then we can just, but this is the cool thing about this is that we can create a new quantity that we'll call A, which is m plus C at the full state minus m plus C at the basic state. So these are constants. These are both conserved quantities, and the a is 0 at u equals 0 because of the constant, and the first variation of a is 0 because of this construction here. So this is both conserved and locally quadratic. In the disturbance. So that's great. Now we have a conserved quantity, which is something like what we would have had in the canonical system. So you can get something that has these nice properties by mixing in the characters. So you can think of these things as a Lagrangian invariance in a way. So you can argue that the whole the evolution is on a surface defined by these Casimirs being constant. So it's like if you constrain to lie on the surface, then you get something quadratic. So you can think of it as like a Lagrange multiplier.
Where's the C coming from? Why is it not just minus m?
Well, if I get m minus m, I just get 0, which doesn't. Well, that's true, but it's true but trivial. I can do something with this, as I'll show you. This is only locally 0. It's actually non-zero as you go away, because if I expand this, this only holds. Oh, sorry, I should have said, yeah, very important, u equals u. So this only holds locally. So once I move away from this, I will get something non-zero. But of course, if I pick m, then I just get 0 everywhere. That's the yeah. This thing. Only if J is invertible. But if it's not invertible, then it'll be linear. But so there's a kernel here, so it's linear. But fortunately, I can find I can always find a Casimir that will match that linear direction, and I can cancel that and then get something. So it's really analogous to Lagrange multipliers that I think you almost know about.
I mean, you couldn't really pick C to be minus n because n is not a Casimir.
Well, it wouldn't. Hey, welcome to Oliver. Well, it wouldn't. I mean, you could, but it would just give you 0 everywhere, which I mean, is of no interest. I mean, of course, you can always satisfy 0 equals 0, but I don't think that's a very interesting.
N is not in the set of Casimir's. N is
It doesn't span the kernel, right? So I mean, that's right. It wouldn't help you. Yeah. Okay. Now, just what was I going to say about this? Was I going to say something? Well, maybe not. We'll just go on. Okay, so this is a very general property, and actually, the really nice thing is this is finite amplitude. So there's no linear approximation here. It's fully general. Okay, so now we go to the beta plane, which is why we wanted to do all this. So we've already said that the functional derivative. So now we have a q, which is omega plus beta y. The vorticity with the beta effect, and you can you get the dm dq is y, and dc dq is some. I'll write it this way: is the derivative of some function, arbitrary function of q. So this is say infinity of Casimirs. And now we can. Now we just follow the recipe. So we consider a disturbance is how much more do I have? I may have to switch to the. Oh my goodness. Somehow I've done well up to now, but somehow okay. To an X invariant basic state. It's because I decided to talk about psychology and climate change, which kind of took some time away from me. So we would write that, let's say, as q naught of y. So if we want, so so if I run this, I want the first variation of dm plus c to be 0 at q equals q naught, and that tells me that c prime at q naught is equal to minus y. Okay, so I've got a. This is actually really this is so this is defining what the Casimir is implicitly in a way, as you'll see, because actually. There's a relationship between q naught and y. So this, and you can treat this now. You can generate a function, as I'll show you in a second, where, well, let me just step through it.
what actually you would arrive at q is a function of both x and y.
Well, then you don't have a translational symmetry, but you can, but you have a temporal symmetry. So in that case, then you would use a pseudo energy, for example. Yeah. Okay, so we just apply this thing. So A is this plus this minus that plus that, and I think we have pretty much all the pieces. So we have, first of all, y times q. That's m of the full state minus m of the basic state. So minus y times q naught, and then we have the Casimir at the full state minus the Casimir at the basic state. So we have plus c of q minus c of q naught. So that's really just a definitional. So let me group a few things. So I'll just group. So I get y times q minus q naught, and then I would. So the thing is, I've got a definition of the Casimir in terms of the derivative. So, but here, fortunately, I have a difference. So I can just write this thing as the integral from q naught to q of c prime of q tilde dq tilde. two pages stuck together, I thought I was going to be okay, but so you can write this out. Maybe I won't go through it step by step, but you can write it as the integral from 0 to q minus q naught of big Y q naught plus q tilde of big Y of q naught dq tilde dx dy, where big Y of q naught of y is equal to y, which defines this the function big U. So there's as long as you have a relationship between q naught and y. Now, of course, there's issues if it's monotonic. This is all very fine. If it's not monotonic, then you have multiple branches and so on. But this, in the case that we're going to typically look at, this thing is negative definite. So it's just a bit of algebra. You should be able to go from this to this with the definition of the Casimir there. Negative for dq naught by dy positive. So this is the case with the beta plane in general for small enough amplitude flows. And so you see that if the gradient of q naught is always positive, then this thing is always going to be an increasing function. Y is always an increasing function of q naught, and then you're integrating something that you'll get something with a negative and quadratic. And the small amplitude approximation, if you just take a Taylor expansion of this, is minus q. This is of the density minus q naught squared over 2 times dq naught by dy. Now let's just say I won't go say more of this, but because this is finite amplitude actually, and because it's signed a definite, you can define nonlinear stability, like strongly nonlinear, not just weakly. So I've got various examples in these Woods Hole lecture notes, but we won't go into that. And finally, okay, I think what I'll do is well, okay, I can write one more equation maybe. So of course, if you take a q to be q naught equals zonal mean, if we're thinking now of the atmospheric case, then q naught is equal to q bar, and the q prime is then q minus q bar. This is like what we would call it the deviation from the zonal mean or the eddy. Then we just get the zonal mean of this becomes minus q prime squared over 2 dq bar dy. So this is, some of you may recognize this as the negative of the Elias and Palm, something called the Elias and Palm wave activity. Okay, and the nice thing about this is that this is a general principle. So you do this in a stratified flow, you get also an EP wave activity, and it's all coming from this Hamiltonian structure, Noether's theorem, and the Casimirs. And just maybe the final thing is to say the sign of, before I go to the board, the slides, the sign of this quantity corresponds to the intrinsic frequency of the Rossby waves. So actually you can see that if Qi is positive, like in the beta case, it's negative, as we've already seen. But if you had a negative PV gradient, then you get a positive sign, and that, of course, it's a positive intrinsic frequency. And this is no accident. You can show this. Actually, yes, what I was going to mention quickly, Hank talked about collisions of eigenmodes, and there's quite a nice theory in the linear, quite a nice Hamiltonian view of instabilities involving collisions of eigenmodes, all relying on this pseudo energy and so on. Oh, well, I meant frequency, but I mean it's going to be, well, I think of it with positive k, so I don't think it's going to be the same. Yeah. Okay, I think I should switch to the slides, and I'm sorry I didn't get a little further on the board. Can we but I'm almost there. But I think you're right. It should be phase speed in this case, strictly speaking.
This type of pseudo momentum, is it related to Stokes drift?
Maybe Oliver will talk about that next. I don't know if he'll talk about it next week or something, but let me, because I'm a little short of time. Let's leave that for now. Okay, so of course when I talked about the first day, I talked about momentum budget, right, of the atmosphere. No one talks about the pseudo momentum budget of the, well, maybe Lay would, but most people don't talk about the pseudo momentum budget of the atmosphere. So we have to relate pseudo momentum and momentum somehow. This is the zonally, so as zonally average zonal momentum equation on the barotropic beta plane. So we have d by dt of the zonal mean u bar, and if you write this all out, we get we have the quadratic, advection terms, which can be written in this form. You got a correlates term and you got a pressure gradient term. Of course, when you average an x, this term goes away. In the barotropic case, the v bar goes away, and the d by dx goes away, and actually the mean part, because the v bar goes away, and all you're left with is this equation here. So this is just a very simple relation that the zonal mean flow can changes through the eddy momentum flux convergence. And then if you write this out again and you add and subtract terms, I won't go through it, but it's just algebra. You can show that this can be written as a potential vorticity flux. So these are kind of very important properties. So you can understand wave mean flow changes in the momentum world as convergence of eddy momentum fluxes, or you can think of it in the PV world, where it's related to mixing of PV. And of course, these are equivalent because of balance conditions. Okay, now how about the eddies? Can we have an equation for the eddies? Well, if we take the linearized potential vorticity equation, we have, so d by dt of the perturbation, q prime. We have only the linear, so there would be, of course, a quadratic term, but if we linearize, it's just the zonal advection or the Doppler shift term, and then we have this term, which would be the beta effect. So for Rossby waves, this is what I wrote down to get the Rossby wave equation, right? And you get the Doppler shift term, and then you get the beta term, and this is what gives you, in the end, the Rossby waves. So as long as the gradient of the zonal mean q is non-zero, of course you can divide then, and you get an equation for v prime. You can then multiply that by q prime, and you see that this is just a constant. You can absorb the q prime in here, and you can absorb the q prime in here. The x derivative then goes to 0 when you take the zonal average, and you're left just with the time derivative. So you can relate this PV flux to minus d by dt of this quantity here. Or our wave activity, this is exactly our wave activity, so this is just d by dt of the A. So actually there's a relationship between the mean flow acceleration and the wave activity change, which goes back, it's called the Taylor identity, it goes back to G.I. Taylor. So it's a very old relationship. So what we have here is then we can think of eddies in terms of momentum fluxes, but we can also think of it in terms of wave activity. And it turns out this is because of course if you want to solve this, you have to close it somehow. So it turns out that it's much more easy to understand the maintenance of the westerlies from looking at it from this point of view, which is the whole point, because there were lots of arguments about the maintenance of the westerlies for a very long time based on the momentum equation alone. Yes, well, at least in the adiabatic case, but I'll show you in a second it doesn't have to be. Now, the reason this is important, of course, we're talking about, I'm talking about barotropic dynamics, but I'm talking about barotropic dynamics applied to the atmosphere. I've already said that in 2D turbulence, we have to have a source, which is baroclinic instability. So we have to bring in the baroclinic dynamics at the end if we want to look at this, apply this theory to the real atmosphere. So it's important that the same stuff all works for stratified quasi-geostrophic dynamics. And you get an equation. So this was a very simple equation. Du dt is just v prime q prime. in the stratified case, you get something a little more complicated, but actually not that much more complicated. You get this operator here, which is an elliptic operator. S is a static stability, rho naught to density. So we have a vertical part and a meridional part, and then d by dy squared here. So you can see if this wasn't there, I could just get rid of the d squared by dy squared and get back to the same equation. But in the baroclinic case, we actually have this elliptic operator on the U. So it's the same physics, but the zonal wind response is not just a local one, it's non-local. And that's because if you apply PV mixing and you just change the wind, you're going to be out of balance, right? Because if you change the wind without changing temperature, you're going to be out of balance. So there's a classic theory that goes back to Eliasson, I guess, in 1951, where you can find there's a unique solution which has a circulation as well, a meridional circulation, which spreads out the response and changes not just winds but also temperatures in a way to restore balance. Of course, you could just the simplest way to do this is to solve the PV equation and then just invert PV, and you get the same answer. So it really follows from potential vorticity inversion, the fact that all the fields are slave to the PV. So you can write the conservation law. So pseudo momentum is conserved, but here I was talking about integral relationships, but it has a local form, and you can write it this way with a del dot f, a divergence of a flux, and that in this case is just this quantity here. And now I've allowed myself sources and sinks, and then if you want to apply this to the atmosphere, as we'll do in a second, you have this operator on du dt, and then you just so we have the same equation here, but now I go to that's just the divergence of this wave activity flux, and then I go to this equation and I get these two terms. So the case I showed before was the barotropic case where we can get rid of the L and the d by dy, and we didn't have an S, so it was just du dt is dA dt. But in the general case, we're going to have first of all these operators, but also an S here, because of course waves are forced and damped. So actually, when I used to work in Hamiltonian stuff, the first question always somebody would say, "The real world isn't Hamiltonian." I don't know if you get those arguments, Oliver. Of course it isn't. But the thing is, it's a way to handle all the nonlinear advective nonlinearity and the wave mean flow interaction part. But you can always bring in the dissipation somewhere, and so here it'll come in here. But the idea is that then the mean flow changes. You can only get a mean flow change either if the waves are growing or decaying, a wave transience, or there's a conservative effect. And this is a very famous called the non-acceleration theorem. It'll become a sink. Yeah, that's right. But it's not a damping of the mean flow. It's a damping of the waves, which then induces a mean flow change. Do you mean? Oh. Right. So maybe if I understand you correctly, so we're going to find out. We're going to see that this S is connected with wave dissipation, but we can think of it in a higher Reynolds number limit, and the amount of dissipation is independent of the viscosity in the high Reynolds number limit. That's what you're referring to? Yeah. Yes. Yeah, that's a good point. Okay, so now we look at the atmosphere. In the atmosphere, we can generally assume that the PV gradient is positive since Q is dominated by beta. So the Ross waves have a negative A. They carry negative pseudo momentum. For historical reasons, the EP wave activity is defined with a plus sign. So you just have to remember that EP wave activity is negative pseudo momentum. So just you can say if we force Ross waves somewhere and they propagate somewhere else and they dissipate, then where they dissipate, they're actually transferring negative pseudo momentum, so they will exert a negative torque. And then, but you have to conserve momentum in the whole system, so that implies there must be a positive torque in the source region. And this was, I think, for me, a beautiful example of this was a lab experiment a long time ago by Jack Whitehead at Woods Hole, where on the set this tank up to have a beta effect and then dropped in a dye, but had a stirring underneath, which generated no net momentum. So there was no net momentum input to the system, and the initial dye state was something like this, and then over time you saw that the flow here became retrograde. The stirring region was in here, and you get this prograde flow. So this is a nice real-world demonstration of this effect. Maybe I'm going to be going too fast now. So in the atmosphere, of course we've talked about synoptic sail Rossby waves and how they're generated in these storm track regions, and they're generated within a jet region. So in a way, if you just have a very simple argument, this is from Valence's book, if you stir here and the waves, of course the waves have to propagate away just by causality. Well, if they propagate anywhere, they propagate away. And then, so where the Rossby waves propagate, you have a momentum convergence in the source region and a momentum divergence in the braking region. So that's the eddy-driven jet.
Or the argument relies on the conservation of pseudo momentum,
Mm-hmm.
but then if you have dissipation, like internal wave breaking, stuff like that,
Yeah.
it can break this symmetry, the symmetry underlying.
Well, of course, you don't conserve in the end. So, but the idea is that you would conserve if you imagine a kind of a very simple case. You have a source region, and the waves propagate, and then you have a sink region where the waves break. So you assume that it's a conservative here, but of course you don't assume it's conservative there, and that's where this S would then come in. Okay. So it is part of the theory. Of course, if you have dissipation everywhere, it probably isn't terribly useful. At least, but the reason it's useful is because you can get non-local effects, teleconnections essentially through the waves, and the waves are conservative through this piece of it, and then sure, then they will dissipate, and then it'll come in here. So if the waves grow, and then so well, I think we'll see how this. I think I have another sign of this. So just to say, another way of looking at this is that for Rossby waves, the sign of the group, you can show easily just by some algebra that the sign of the group, the meridional group of velocity is negative the sign of the momentum flux. So waves propagate with a group of velocity, so if they propagate in one direction, the momentum flux has to be in the opposite direction. But you can also just understand it from this pseudo-momentum argument. Or you can understand it by down gradient PV mixing. So you can argue for the sign of this Q prime V prime based on the PV gradient.
In the first lecture, you showed the location of maximum eddy activity and the location of the jet maximum. And in the southern hemisphere, these are not in the same place. So how can one understand that?
Okay, I think I'll come to that shortly, actually. Next slide. Okay, any questions about this? So this is just the idea that if you can force, in the barotropic case, we just force the waves, and as long as they're Rossby wave, of course it's nonlinear, but they have a Rossby wave character. And if they propagate away and break somewhere else, then you're going to get acceleration of the source region and deceleration of the sink region. So I argued in the first day that the momentum flux actually is out of the tropics into the middle latitudes. So that's why we have tropical easterlies. But Brad showed a simulation where he was steering in the tropics, and in that case he got westerlies in the tropics. But that's because he's steering in the tropics and the waves are propagating away. And I think some people argue that under certain extreme paleoclimates like the Eocene, there might have been, wave, because in the present day climate, of course, there's Rossby waves propagating out of the tropics because we're interested in teleconnections from El Nino, but there's more Rossby waves propagating in than are propagating out. That's why we have westerlies. But that doesn't have to be true in general, and it could be true in certain paleoclimates that the momentum convergence is into the tropics. Yep.
So in the beta plane case, if I force locally in the somewhere and have dissipation, you can see this picture very clearly. But when I force everywhere, I still see jets, and then how does this narrative comes along?
Yeah. Okay. Well, I'm not really going to talk about that actually. So I think that's where maybe Bill Young might get into this a bit more. So, yeah. So that's a very good question. Obviously, if you with the atmosphere, it's kind of easy because we have a baroclinic zone, and so we have sort of a starting point. But if you and the system isn't symmetric in Y, of course, because the pole and the gradient. So usually in the atmosphere, you think of it not as as generating a mean flow to zero, but more as a sharpening. So you can think of this as a sharpening and strengthening of the jet rather than building up the jet from zero. But if you're thinking about a case where jets emerge, say, in some planetary atmosphere and you don't know, then you have to come up with some arguments. So I will mention that, say a little bit about it briefly tomorrow. But yeah, of course it's a more complicated problem because then you have to solve the full feedback problem. Mm-hmm. Well, Kelvin waves can't directly because they don't propagate because they're trapped. So Kelvin waves do transfer momentum, but in the vertical. So then you can get non-local redistribution, and it's the same, and then it's a positive force. So the same principles apply for any wave, of course. Well, not in the zonal mean, but they could force it locally, conceivably. Yeah. Other locally in the vertical. Okay, so of course we're not. If we want to look at the atmosphere in the end, it isn't barotropic. So we have to understand how this fits with the whole picture. So there was a very famous set of experiments by an American experiments by Simmons and Hoskins in '78. What they did, they set up a spherical model. Actually, it was in wave number 6 symmetry, and they began with the primitive equations. They began with the Charney most unstable mode and let it rip. And what happens is that you got a Charney instability. The waves grew through the normal baroclinic instability, but then the waves saturated, and then they dissipated. And they dissipated through barotropic mechanisms, basically through the horizontal shear. So it's called a life cycle. The waves grow and decay, and but the growth is baroclinic, the decay is barotropic. And then Eben, Hoskins, and McIntyre. This is in this paper. So this is now after deriving these EP fluxes, which were being derived around the same time. So the EP flux is the del dot F, or that's of course the divergence. So the arrows. This is the EP flux divergence. So this is a cross section. This is latitude here. This is pressure shown here, but on a linear scale. And what we see is that the waves are generated. We have a source region here of the wave activity, which is right by the surface. That's the Charney mode. The Charney mode grows in the baroclinic region. It grows with steering level in the lower troposphere. But then, so that's our source region, and then we have a sink region because the waves propagate upwards and equatorward. So I was in this Vallis picture. We're just looking at the latitudinal part. In fact, it's up and out. Okay, and then if you compute what the mean flow changes from that, this is a paper by Haynes and myself with this Eliason balance theory. So I said it's a non-local inversion. So in the Whitehead experiment, we get a positive forcing here and a negative forcing here, and that just drives a mean flow. But it's a 1D problem because it's barotropic. In this case, it's a 2D problem, so we have to solve this inverse problem. And you'll see that there's an aspect ratio in here that there's an FF that appears in here. So there's various geometric factors, and it would maybe seem surprising to you that the wind changes here are not coming from this term, but from this term here. But that's just because it's an anisotropic operator. So it gives you a very deep response. And so this acceleration from the wave source region actually accelerates through the whole troposphere. And the deceleration in the sink region decelerates through the whole troposphere. So the response is very barotropic, just because of the aspect ratio in the if you transform coordinates. Yeah. convergence, because it's a negative divergence. Yeah. So the EP flux convergence, of course, EP flux is negative of the wave activity. So it's yeah, because it's minus the pseudo momentum. So this, if you put that into the Eliasson equation, you get this response, and you put this, and this gives you this term. So this is acceleration. This would argue that the net effect of this eddy is as you go through the whole life cycle. So sure, as the eddies grow, they're extracting energy from the mean flow and so on. But in the end, once they decay, they provide a feedback which is barotropic, and they act to accelerate the flow all the way down. And there's a deceleration on the flanks, and a little bit of a deceleration possibly here as well. But so this is the maintenance of the westerlies. So this is, if you just look at this as a cross section, this is kind of this Vallis picture. Then in that paper, they looked at observations, which at the time was obviously fairly limited. But they had 11-year averages, and this is the EP flux divergence in the atmosphere. And what they found was that there were two regions. So there's this region here, which looks a lot like this one here. But there's also a region here. And then there's another region here. This is H for high. So this is an opposite sign. This is an EP flux divergence, which implies a source of Ross waves, if you think of the theory I've just showed. I won't go into that because there's another story behind that. Have a paper with Thomas Berner on that. It's probably a curiosity, but maybe there's something deep. I'm not sure. It's to do with finite amplitude effects and transport of PV. I suspect if you do this properly, like Ley would do, then maybe this thing goes away. Anyway, but the main thing is we have this. It's very small anyway. The main thing is we have these two regions of EP flux convergence in the upper troposphere. So
excuse me, Ted. So I mean this conservation of wave activity, the Eliasson, palm flux, and so on and so forth, they are all equivalent to the material transport of potential vorticity, I guess.
No, because it's it's Rossby waves, so
It's
that's not equivalent. I mean, you can derive it from the material conservation,
Yes.
but you can derive everything from the material conservation because
Yes.
that's the equation. So, but of course, it's not physically transported. These are waves, so there's no physical transport of PV from one region to another. It's just waves, right? So, I mean, of course, it's consistent with material conservation, but it's a non-local effect through wave propagation. Yeah.
Thank you.
Okay, so it turned out that they made some small changes in the mean state, and they found that actually, if they changed the mean winds a little bit, they got a rather different behavior. So LC is for life cycle. So this is the classic case, which is, but this is at day 6. So this is a halfway through when the graves have grown, but before they, I guess, I'm not sure what stage, but so it's not the it's not as clean as this picture here yet, because it's still, the first one was averaged over the whole life cycle. So we see this source region down here and the breaking region up here, but in this other one they called life cycle 2, they get a feature up here. Actually, just as another anecdote, McIntyre anecdote. So when I arrived in Cambridge as a postdoc in '84, and Michael, we're going to work on life cycles, and he said, well, but I just have to finish this paper. So you can start as soon as I've got this paper finished. Well, I got into Hamiltonian stuff, and it never really came back to, except with this other work with Peter at the end. And it's a good thing I did, because the paper they were just finishing in 1984 got published in '93. So, okay, so if following this hierarchy of model ideas, you can match up this feature with this feature here, and you can match this feature with this feature here. So the implication is the atmosphere can exhibit both of these regimes, and basically the waves can break either on the poleward flank of the jet or the equatorward flank of the jet. They tend to break on the equatorward flank of the jet. So I'll show you that in a second. So I think this is understood by most people as the explanation, not only first of all for the maintenance of the westerlies, but for these two regions. And if you so you see that this feature is in the upper troposphere, and this feature is a little bit in the middle troposphere. So Randall and Held in '91 had the courage, I guess, to look at the observations at the time in terms of the so they did a phase speed spectrum. So the EP flux is a quadratic quantity, so you can take a spectrum. It's a covariance spectrum, and you can write that not just as a wave number or a frequency, but in terms of a phase speed. And they plotted that. This is the winter time, December through March. A divergence of the EP flux at 200 hectopascal. So this is this feature. This will be cutting through around here, and at 500, which cuts through down there. And what you see, and plotted on top of this, this is the wind, the mean zonal wind. So these are the mid latitude jets, and at upper troposphere and middle, and this is the EP flux I guess it's a convergence. So what you see is that the waves are breaking, or they're dissipating. That's all we know from this, is that it's dissipating. But in fact, they're breaking, and they break because of critical layer effects. Now, I don't really have time. How many of you know about critical layers? Most of you. Okay, good. So you know that basically, as the phase speed of a wave approaches the mean flow speed, you get a critical layer, and the amplitude of the wave increases, so the waves are going to break. And if the waves have in the infinitesimal limit, they break at a critical line, but in the finite amplitude case, they're going to break before they get to the critical line, and it's going to be in a critical layer. So if you imagine a source region somewhere in here, then these are the waves that are breaking on the equatorward flank of the jet, and they're breaking through critical layers, and these are waves breaking on the polarward flank of the jet, and they're also, so these are, so in fact the waves are breaking through a critical layer. So the wave theory is important. You're not going to get this through just a turbulence approach, not recognizing PV and its importance for this problem. This is for northern winter, northern summer, summer. So it means that the jet shapes the, so if you write the equation of the forcing of the jet by the eddies, you would say, well, okay, the eddies shape the jet. But this comes back to the question at the back in a way. But the jet also shapes the eddies, because if you want to know what the forcing is, you have to know what the jet is. And you can see that the jet affects the forcing. And I think I'll say a few words tomorrow that, for example, effects of El Nino or climate change, they can shift the winds a bit, and they can shift where the critical layers are. So there's a feedback there. So you can't assume that you know the waves. You're going to have to solve for the waves somehow. And so that's where this feedback comes in. So McIntyre had this phrase called the wave turbulence jigsaw puzzle, that we have a mixture of waves and turbulence, and they somehow fit all together, but we have to look at the combined problem. And I think, okay, maybe this is my final slide. So then if we come back to this picture, which I showed Bowman Lee, but it's a similar plot. This is from Valence's book. So we come back to the fact that the eddy momentum fluxes are directed into the jet. This is for the northern winter, southern summer. We see that there's actually, in the southern summer, it's perfect in the sense that the convergence is right on top of the jet. That's an eddy-driven jet. In the northern hemisphere, it's not perfectly aligned because this jet, it's the winter, so it's involving the Hadley circulation. So it's not an eddy-driven jet per se. It's a mixture of the eddy forcing and the Hadley cell. But the way to understand this is through the wave activity fluxes. So that's where I'll stop, I think. Yes, Noah.
So the vertical propagating waves, the vertical part of the UP fluxes, and the height where they propagate is determined by these critical layers. But what determines the height of the U prime V prime part of the horizontal flux? Is it the same?
Well, actually, it's the critical layers are in a way determining I think of it as if you look at this picture, you think of it as determining the meridional. But of course, it's in the meridional from vertical plane. So I guess if you looked at this kind of a picture, you could look at a refractive index and things. So they're propagating. They're going to hit a critical layer, but from this barotropic theory, we think of hitting it sideways. But of course, they're hitting it up in the vertical as well. So I think some of this is still open. In fact, I do remember that one of the one of the reasons that this paper took so long to write was that they were trying to explain the propagation through ray tracing, and they could never make it work. So it just didn't seem to be a practically useful tool. So I think there's still some open questions about that. Really, I'd have to say.
So
I just was wondering why in the southern hemisphere, on the last slide, the horizontal fluxes are in the mid-troposphere compared to on the northern hemisphere. They're basically in the tropopause level. Right?
Well, no,
So
but this is the same. This is the same. That's the same. So it's really symmetric. And as I say, if you look here too, the upper tropospheric fluxes are on the subtropical side, and the mid tropospheric fluxes are on the poleward side. And if you look in the other time of year, it's the same picture. So yeah, it's the same there.
So at the beginning, you discuss wave versus eddies, and you say that. So here, the end of your talk is mainly related to waves. Does I understand well?
Well, I'm not. Obviously there's, but there might have been a few different reasons why ray tracing doesn't work too well, because you don't have very good scale separation things. But once you're deforming PV at these are big amplitude things. If I showed you pictures of these are not linear waves in the sense that they don't look like linear waves, but the character is still in there. So I don't know. Like I know in theories of turbulence that like Greg Holloway and probably Rick actually had done some stuff on the Rick Salmon. You can bring the beta effect into turbulence too, so it just shifts some of the frequencies. Now, are those waves, or is that just turbulence in the presence of beta? So I'm not sure I'd want to call them waves. As I say, nobody would call these waves really, because you certainly can't really trace them as a wave, not like a stationary planetary wave or something like that. But it's clear that the wave character is coming in. So I think it's turbulence colored by this wave aspect. But you definitely do get transfer at a distance. I mean, if it was only turbulence, you wouldn't be able to connect regions. I think with well, no, that's not even true, is it? Because you've got PV inversion. I'm going to say something wrong, but so yeah, I don't think that's a useful distinction. As I say, so people have yeah. I don't think anyone's managed to make it work to use wave properties to really explain any of this.
This might be a naive question. So we talk about how synoptic scale waves depend on the zonal mean, but how do planetary waves and synoptic scale waves interact?
I'll talk about that tomorrow if you can wait. So we come back to the final
So it's not that
piece
naive.
of the puzzle.
Okay, so you mentioned that the height of the critical layers are different in subtropics and mid-latitudes. Are there like simple explanation for that?
Well, it's just because I mean, the way I would explain it is just by looking at these plots. Basically, that if you go, well, I don't know, because you can take the view, and actually Dave Lorenz, who's no relation to Ed Lorenz, has tried to use what he calls Rossby wave chromatography. So he takes a spectrum and then tries to figure out if they're propagating, equatorward or poleward, and then where are they going to break just from the phase. So I think it's just they're going to meet. I don't know exactly what the answer would. I guess it's because maybe the phase speeds are lower or something. I haven't really thought about that in detail. But they're obviously both breaking at it's critical layers here and critical layers here. Uh-oh. I could repeat the question, but I guess we're almost there now.
All right. So for the oceanographers, they in their model they don't resolve those waves, and instead they parameterize them through Gent McWilliams parameterization. So basically that was based on the same set of equation eddy mean flow interaction, the momentum conservation law. Now, I was wondering, I mean, for the atmosphere, certainly we resolve all these waves very adequately. If we if we think backwardly, if we take a very crude resolution model, like maybe 10 points for the globe, for the entire hemisphere, and we intentionally don't resolve those raspy waves, could we actually have a working machinery that using those parameterization to do this job?
Well, actually, that was the first plan for the postdoc in Cambridge, because at that time people were using zonal mean models or just models with planetary waves as kind of simple models, but never got around to that. I don't know about I don't want to say much about the ocean case because I don't know much about it, but I know although the parameterization is based on these ideas, the CP flux, so it means at least you're doing things in a dynamically self-consistent way, but you still have to specify what that Q prime V prime is. How do you do that? So you need a theory for the eddies, and in principle, what you would have to do is carry a separate equation. It's like in turbulent boundary layers, people have a turbulent kinetic energy. You'd have to have an equation for your low resolution flow, and then it'd be like this quasi-linear kind of theory that Brad's talking about, and then you have a separate equation for the wave activity, and you're going to have to somehow close that. So it doesn't get around. It doesn't mean that you got the right answer until you get the right eddy forcing. So one of the difficulties with this whole theory, in a way, although it's so we have this is a really exact this is QG, but you can write this in primitive equations. It's a really rigorous theory, but how do you specify this? So we have this equation, so we have to solve this equation. Well, there's not obvious way that you could say you could do ray tracing maybe in certain limits. At least critical layer control seems to be a pretty good principle. So that's something which is robust, nonlinear, fine amplitude, and so on. So, but there's there's no theory of all this, and so you'd have to sort of close it somehow. There have been attempts to do it, but that would be a non-trivial exercise.